Okay, we're happy to have Sylvia Serfaty, who will tell us about the microscopic description of Coulomb gases.
Okay, thanks a lot, and thanks for the invitation. Can everyone hear me well? Yeah. All right, so feel free to interrupt if you have questions. So I'm going to be talking about Coulomb gases. I apologize to those of you who've heard me talk about this already, maybe several times even. But we're going to be talking about systems with Coulomb interaction. So you look at n particles, points or particles, I like to think of physics, in a d-dimensional space. And there is the sum of a pair interaction here with a repulsive interaction, which is very specifically Coulomb, plus some confinement potential here. Okay, so in dimension 2, Coulomb is minus log of the distance, and in dimension 3 and larger, it's 1 over distance to the d minus 2. Of course, this is up to multiplicative constants, if you want. And some of the things I'm going to talk about also work in the case of non-Coulomb interactions. Very precisely, you can consider minus log in dimension 1. That's the log case. Or you can consider 1 over distance to the power s in general dimension. But the power here has to be between d minus 2 and d. So it's d minus 2 is Coulomb. All right, so this is sort of super Coulombic. I'll call that the Reese case. The potential V here has to grow sufficiently fast at infinity. Let's say it's smooth. Of course, you can think of V quadratic as a very famous example. And we consider the associated Gibbs measure, which is the one with this density exponential minus beta times the energy, divided by the partition function z and beta. And here I've included a slightly unusual, maybe scaling of the temperature by putting this factor n to the 2 over d minus 1 in front. It's actually not a loss of generality. It turns out to be a good scaling in order to see interesting effects at the microscopic scale. If you're used to working with these log gases in dimensions 1 or 2, in fact, this thing doesn't really do anything. So this is for the Coulomb case, and this is the scaling for the Coulomb case. All right, so motivations for this are numerous, but quite well known, I think. But there is random matrices because the Ginibre ensemble, for instance, corresponds to a Coulomb gas in dimension 2 with confinement potential V, or what I mean rather is that the eigenvalues of the Ginibre ensemble follow exactly this law in dimension 2 with the quadratic confinement for beta equals 2. There is some more general ensembles that are very studied in random matrix theory, which are called beta ensembles. They would correspond to the 1D logarithmic case with general beta. Motivations also come from quantum mechanics a lot, in particular the quantum Hall effect, because then there is something that's called the Laughlin wave function, which takes exactly the form of a Coulomb gas, essentially. Other things like self-avoiding path. And also the Coulomb gas in any dimension can be considered as an important statistical mechanics model. It models in particular plasmas or sort of classical matter, like a sort of classical version of electrons and ions. And it has had a lot of attention from the physics community for that reason. But there's also relations to XY Sine-Gordon models from theoretical physics when you consider Coulomb gas in 2D that would have pluses and minuses, so plus and minus charges. But I will not talk very much on that. So in what I'm looking at here, all the charges are pluses, and they stay together. Well, they stay confined thanks to this confinement potential. Any questions so far? No. Okay, so there is A well-known object in this context, which is called the equilibrium measure, naturally arises when you take the limit as n goes to infinity. So recall that's the energy. So you want to consider a sort of continuum version of the energy here, where now you're integrating against probability densities. Right? So instead of having discrete charges, you sort of spread the charge. And you can minimize this thing over probability measures. And if your V grows sufficiently fast at infinity, there will be a unique minimizer because it's convex. And that unique minimizer is called the Frostman equilibrium measure. I would call it the equilibrium measure. And that works, in fact, for very general interaction kernels. So Coulomb, but also these Rees or even smooth interactions. And what's quite easy to prove is that the energy, of course, scales like n squared, because this is the number of pairs of particles, and there is an n here in front of n terms also. So it's going to scale like n squared, and the millimole energy is just going to converge to n squared, or divided by n squared, just going to converge to the to this E of mu v, so to the E energy of the equilibrium measure. And also the empirical measures of the particles will converge to the equilibrium measure. So that sort of settles the behavior of minimizers in this so-called mean field regime. But of course, what one wants to understand is also what happens for the Gibbs measure, not only for minimizers, but for typical states under the Gibbs measure. So in case you don't know, the equilibrium measure can be explicitly described in some simple cases. For example, when V is quadratic, for all the Coulomb cases, the equilibrium measure is an indicator function of a ball in any dimension, right? So suitably normalized. So it means that the distribution of particles will be uniform in some ball, and it will be, in fact, compactly supported. That's the typical case. And in the one-dimensional log case, the famous example is the case where V is quadratic. Then the equilibrium measure is the semicircle law, and that's the well-known density eigenvalues for GOE ensembles, etc. Okay, so this is like the type of examples we have in mind. We will always assume the equilibrium measure is nice enough. And I tend to confuse the notation, use the same notation for the measure and its density. I hope you forgive me for that. And so as I was saying before, what you care also about is what's going on when there is temperature. And it turns out that the behavior doesn't change very much. So in terms of the average behavior or the limit of the empirical measure, you still see the equilibrium measure, except with exponentially small probability. In fact, that can be formulated as a large deviations principle. The speed here is n squared. And this has been proven in a series of works that are often for the logarithmic case, but in fact, the proof carries over in a much more general setup. You can do it for very general interactions, in fact. So maybe what I want to emphasize at this point, for those of you who know these types of results, is this works because you fix beta and you let n go to infinity, and because in fact, with this choice of temperature regime, it's really the energy that matters. The entropy does not come in and play a role. If you want to see the entropy come up, you have to consider beta that depends on n. So you have to consider much larger temperatures. So we will be discussing a bit of that later. So let me show you simulations of a 2D log gas. So here, the interaction is logarithmic, of course. The confinement, again, is quadratic. And beta is going to change to go from small to large. So beta being an inverse temperature, it means that we're going to cool down the system. And as you can see, the distribution of points is following the equilibrium measure, which is the uniform distribution in a disk. right? So you should see the points uniformly distributed in a disk. So let's now decrease temperature. It's still kind of well distributed in the disk, and you see that as you decrease the temperature, so the macroscopic distribution doesn't change very much. It's always the equilibrium measure, but the microscopic distribution changes and gets sort of more and more rigid, right? Until you get to very, very large beta, where you can start to believe in some form of crystallization in those pictures. So this one maybe is a bit convincing, right? So there is some sort of crystallization happening at very low temperature. Okay, so this is the type of phenomena we want to understand, and one can phrase it into several questions. So one natural question is you want to understand basically the deviations or the discrepancy between, for example, here, you're counting the number of points that are going to fall in a certain ball minus what the equilibrium measure distribution would tell you. So you know that the empirical measure looks very much like mu v. So now when you multiply by n, you're counting number of points. You're counting n times the integral of mu v in the same ball. And you're expecting that this is actually small compared to the size of the ball. So at least should be much smaller than n times RD, which is how many points should be in that ball typically. But the question is, for which R can you prove that? Right. So in this setup, so I'm going to try to draw. You have many points. So you have a macro scale, which is the size of your patch of points. This is size 1, and of course you have a micro scale, which is the sort of interdistance between the points, and that's n minus 1 over d, because there's n points in a volume of size 1. Okay, so is this type of thing true for when you look at small boxes? Is it true down to the micro scale? Is one natural question. And also, next question is, when you look at the configurations at the micro scale, if you zoom, do you see interesting limiting point processes? Can you say something about them, characterize? Can you do something like that, but with respect to linear statistics, so smooth linear statistics, which means instead of counting number of points, let's test against some smooth test function here and see if that is relatively small, and also if that's Gaussian. Question. For which test functions can you prove that? Can the test function be supported on small scales? How does this all depend on beta? And in particular, I would like to allow beta to depend on n, because as I was telling you before, when fixing beta to be a constant independent of n is a kind of an arbitrary choice, and it is can be quite natural to let beta be like 1 over n, for instance, or maybe to let beta be very large as n goes to infinity in order to see other interesting effects. Any questions so far?
Can I ask, is there a notion of Debye length?
Yes, I mean, there is a, if you want, yeah, there's a notion of a screening length, and that's going to be actually very related to this micro scale. So hopefully, maybe what I explain later, you will get a little bit of information on that. Another type of questions that turns out to be very closely related is free energy expansion, right? So the free energy is what you get when you compute log z, z being the partition function, and divide by beta, minus 1 over beta. And there are some very interesting predictions in physics. So the fact that this thing exists or has a limit when you divide by n, as n goes to infinity, has been shown in this literature, Lieb Leibowitz, Lieb Naunhofer also. But what's interesting is to see what coefficients are expected. So there are some now, some relatively recent predictions of physicists here. You see for beta equals 1, for general beta, that tell you that the free energy has an expansion that contains first the power of n squared. So it's n squared times this energy E of the equilibrium measure that we saw before. So that's actually quite easy to show. That's not surprising at all. We can prove that just with the large deviations principle that I showed you at the beginning. Then there is an n log n term that's, because we're in dimension 2, it's very specific to the logarithmic interaction. You should get an n log n term, also not very hard to guess and to prove. And then there should be an order n term with a coefficient depending on beta. And in fact, what we can access now is this thing. We can describe this coefficient. So I will show that to you a bit later. But they continue and they tell you that after that, there should be a power n to the 1/2, a log n term, order 1 term, and then some negative powers of n to the 1/2. That's dimension 2. Dimension 3 or higher is not even a conjecture. And the other thing is that these coefficients here in theoretical physics have some interesting geometric interpretations. So what the physicists do, in fact, is they put that on a manifold. So they like to think of the partition functions of Coulomb gases on Riemann surfaces. And what they do is they vary the metric. But really for us, varying the metric is the same as varying the external potential V. So you just change one V to another and you look at the ratio of partition functions and you compute the log. And then when you do that, they say that all these order n to the 1/2 terms, log n term, and log n terms should actually cancel when you make the difference. And you should only be left with n squared and order 1 and then order 1 over n. And the coefficients that are sitting in front of these powers have these geometric interpretations in terms of the metric. So this S2 is actually just like our E, so what I call E, to the equilibrium measure energy. So in the geometric language, they call it the Aubin-Yao functional. The S1 is just the entropy for us, but they call it Mabuchi functional. And the SL, which we don't have access to at all rigorously, they call the Liouville functional, and it's related to something called gravitational anomaly. But okay, so these things are calling for some proofs, and we still have ways to go to do that. Okay, so I think this was my part about motivations and questions, and I'll start to give you a little bit of results, unless you have any questions at this point. So first result that's a little bit older, but I'll describe briefly, is some work we did with Thomas Leblay in particular, where we described an LDP for the empirical fields of these Coulomb gases. And so to describe it very roughly, this is what you want to do. So you have here your sigma, which is the support of your equilibrium measure, and most of the points fall in there. Or maybe there could be some outliers, but not so important. And then you have your micro scale, which is n to the -1 over d. And you want to take some blow-up centers, here these crosses, and you want to zoom at the proper scale, so it should be this, UVN to the 1 over d. And when you zoom, you see a configuration of points, which, the factor is chosen so that the density of points is 1 in all these blow-ups. So there should be 1 point per unit volume, typically. Okay, so for when you let n go to infinity, these clouds of points are going to grow and become infinite. They'll occupy the whole space. And we're going to define an energy for these infinite configurations. So C is some infinite configuration. My interaction energy will be called W. It's a Coulomb energy for an infinite set of points. But in order to define it properly, I have to think of my infinite configurations as an infinite sum of Dirac masses or infinite sum of discrete charges neutralized by a uniform background of density 1, or so with charge -1, uniform charge of -1, and that's what the physicists call a jellium. So this is a well-known object in physics. It's a sort of infinite Coulomb gas with a neutralizing background. They also call it a plasma, infinite plasma. Okay, so for each blow-up configuration, I will compute W. Each configuration has its own W, and what you have to do then is you have to average by averaging over the blow-up center. So you have to sum basically over all these over all the points where you blow up, and that's W bar. I won't give you a very precise definition, but something will come later. So the result, so before giving you the result, let me tell you a little bit about this energy that I haven't defined. Okay, it was introduced in these papers. We can show that, but what's going to matter really is what's interesting is what are the minima of W? How do you minimize this energy? First question. So minimizers look very uniform in some sense. So we can quantify this, some results. And then there's something more precise. If you're in dimension 1, the minimum is just to put your points on a lattice Z. Remember, everything's normalized, so the number of points per unit volume is 1. So the best way to put your points in dimension 1 with density 1 is to just put them on the lattice. So W seems to be something that favors very regular arrangements of points. And in fact, so in larger dimension, there's something very pretty fascinating, which is that some dimensions are special, and the special dimensions are 2, 8, and 24. And it's in 2, 8, and 24. Yeah.
Can I ask you a question just to, because I don't know the definition of this W really, but in dimension 1, so we are back to, let's say we take random matrices, GUE, okay, and it falls into this. So usually
I'm at beta equals infinity.
Ah, that's okay. Okay.
So
because normally it's I see. So this thing is a limit of the usual GUE sign process or whatever. I mean, the thing which is in the bulk.
So it's the limit as beta goes to infinity, because I'm only thinking about the minima here. Yeah. So in the next year, okay, maybe I'll show you the thing right away. You see, in the end, what matters is you want to compare. You want to add the energy W plus an entropy. Okay, and so so the entropy comes into play to compete with W. Okay. So your favorite sine beta that you know is going to be a minimizer of that.
I see.
Okay. So here you should think I'm at 0 temperature, and so I find that I should put my points regularly. And in dimensions 8 and 24, there's something else that plays the role of the lattice Z. There's some special lattices. So E8 lattice and the Leech lattice in dimension 24, which are conjectured by this Kohn and Kumar conjecture to be actually also minimizers of this interaction energy, but of a broad class of interaction energy. So they're actually universally minimized. There's some universally minimizing properties that happen for these lattices, dimensions 2, 8, and 24, and only in those dimensions. And this is a number theory business, right? So this is a business for number theorists, and these guys just proved the conjecture last year. It was really a big breakthrough in dimensions 8 and 24. But I would say, sadly for us who care about random matrices, for instance, they haven't been able to prove it in dimension 2. Although it seems very plausible that's also true. Remains open in dimension 2, and we arrived at this conjecture by different routes, also in works with Etienne Sandier and other people in approximation theory showed this conjecture is equivalent to other conjectures that makes it even more plausible. And dimension 2, it should be the triangular lattice. That's this universally minimizing lattice. And in other dimensions, there shouldn't be a universally minimizing lattice. In a sense, it should depend on the interaction. So if you change the interaction, the lattice should change. And if you go to high dimensions, it should not be lattices. It's a low dimension phenomenon. I can discuss that if you're interested after. A lot to say on that. Okay, so now what happens when we put the temperature back in the business? So you have to express things in terms of point processes now, not just point configurations. So you see here point processes that you know well, the Poisson on the right and Ginib on Poisson on the left, and Ginib on the right, which is the only point process that we know for these Coulomb gases. Right? It's the only case where we know the point process exactly. There is 1D log, which is not really Coulomb, for which we know the limiting point process, it's sine beta. Then there is Ginib, which is beta equals 2 and V quadratic, and that's all. We don't know a point process when beta is not 2, for instance, and in dimension 3, we know even less. And so the result we had obtained with Thomas Leblay, it works for Coulomb, but also for these log interactions in 1D that are quite well studied, and even for Riesz interactions, shows that there is an LDP for the empirical field when you zoom, when you look at these point processes obtained after zooming around moving point X, the LDP is at speed n, and the rate function is this one. Okay, so you take your point process centered at X, and then you average over X, the centering point, and you have the sum of W plus 1 over beta relative entropy of Px with respect to Poisson. Okay, so there's the competition between the two. Now you see W, we think that W, so it's the energy contribution, W wants very ordered configurations, or at least in low dimension, that's what it seems. And relative entropy wants things that look like Poisson, so that really don't interact so much. So of course, these two desires are sort of contradictory. And then the temperature is what determines the behavior. So when beta is very large, you can throw away this term, and you expect this very regular rigid behavior. It's even now a proof, right, with dimensions 8 and 24. Or dimension 1, thanks to this Coulomb-Kumar conjecture. When beta is very small, you should only pay attention to this term. So you can show this way that you converge to a Poisson point process. It's even a proof as well. And in between, there's something intermediate. And in dimension 2, in particular, physicists have some speculations about a possible phase transition that would happen for some intermediate beta and for crystallization in the sense of a change in decay of correlation functions for this system. Okay, so coming back to Gérard's comment, in dimension 1, we know the limiting point processes because there are the sine beta processes. So it's one of the cases where we know. And so what that shows is that sine beta minimizes this rate function. And in the 2D case, the only thing we know is Ginib, but it also must minimize this rate function. Is that clear? No? Okay, we did something like that for this 2-component plasma, the thing where you have pluses and minuses with Thomas Leblay and Ofer Zitouni. Okay, so now I want to move on a little bit and be interested in expanding our knowledge for beta that may possibly be very large or very small. So what I described so far is...
Sylvia, if I may, just to come back to the thing before. So yes. there's another case which might be, dimension 2, but beta equal 1. I mean, the real Ginib.
Yeah.
Locally, it should not be exactly the same, of course, because but there's something happening, for instance, near the real line, which is not exactly the same.
Yeah.
But this should be the result you have here for the for Ginib should be true for beta equal 2. Should be also something like that should be valid for beta equal 1.
Yeah, it's very plausible. Yeah, you just have to worry about this thing near the real line
Yeah.
that adds these
There's a little bit of a
different potential. Right? It doesn't fall exactly in the framework.
Yeah.
But yeah, I agree. Okay, so what I first want to advocate here is the idea of not using the equilibrium measure itself, but a modification of it that we call the thermal equilibrium measure. So, you know, the equilibrium measure minimizes this. Instead, I want to take the same energy, but add a little bit of entropy. So add precisely 1 over theta integral of mu log mu, where theta is a new parameter, which is defined like this, beta n to the 2 over d. So you can do some formal computations, and you can see that this is actually natural. So, you know, like I told you before, at the temperature that you look at, if beta is fixed, the entropy doesn't really come into play. And that's why we see the equilibrium measure anyway. But in fact, if you see how much entropy should contribute, it should contribute exactly that. And of course, if you fix beta, then beta n to the 2 over d is very large, so theta is very large. So this term is indeed negligible, so that's why it was neglected. But when you put it back in there, even though it's negligible, it gives an interesting correction. And this correction allows you to get more precise results. And also, it allows you to treat the case where beta is not fixed, but in fact, what really matters is that theta is large. It's not important that beta is fixed and this goes to infinity. The regime that's interesting is that theta goes to infinity. So as soon as theta goes to infinity, this mu theta, now I have to call it mu theta for lack of better notation, of course, does converge to mu v. We obtain some precise asymptotics with Scott Armstrong on this convergence. But you know, mu v is something that's compactly supported. So let's say, seen from the side, the density is something like this. But mu theta is something that has tails, right? So it's not compactly supported. It has these exponentially, my drawing is terrible, but it has these exponentially decaying tails. And the length scale of the transition here, we prove is 1 over square root theta. Okay, so as soon as theta is very large, this is very small. So it means that, you know, the points, they don't really all stay in the support of the equilibrium measure. There's a little bit of outliers, and the outliers follow this tail. And this introduces this new length scale, 1 over square root theta, which is also this, which is a length scale for, I call it length scale for microscopic rigidity in the sense of this, right? Because this sort of transition layers is of scale 1 over root theta, but we will see just a bit later, it turns out to be also a length scale for microscopic rigidity. So this is an important length scale. Okay. So what happens when you use the thermal equilibrium measure instead of the regular one is you can rewrite the energy in a pretty nice way. So you remember the energy, you have the sum of all these pair interactions, right? So if you wanted to write it in an integral form, you would have it to double integral of w x minus y, sum of Dirac's of xi, sum of Dirac's of xi. But now what we do is we expand around n mu theta. So we do as if sum of delta xi, we say sum of delta xi is roughly n mu theta plus the difference. And you expand. Because the energy is essentially quadratic, I mean, there's a quadratic part and a linear part, there's going to be some very simple computations. The contribution of mu theta is going to give you this E theta of mu theta, where now E theta is my new, the energy where I have added the little bit of entropy. That's my leading order term in order n squared. And then this is going to come out, and this is going to come out. So the reason why this comes out is because mu theta satisfies a PDE. So mu theta being a minimizer for this satisfies a certain equation. It's a PDE. That's how we study it here. And when you plug in the PDE in there, you get these terms. And so now what's important for us, it's this next order energy, which we call F. So Xn is a configuration of points, right? Capital Xn, it's X1, Xn. And mu theta is the background now, that becomes the neutralizing charge. And here you have the total Coulomb interaction of the system formed by the Diracs and the neutralizing charge mu theta. Okay, so everybody interacts, the pluses interact with the pluses, the minuses with the minuses, and the pluses with the minuses, except the minuses are diffuse and the pluses are discrete, concentrated. But you have to pay attention here, you have to remove the diagonal. So triangle complement means complement of the diagonal, because you don't want a point xi to be hitting itself in the interaction. And so that's the next order energy. So when you plug that into the partition function, you see some term comes out as a constant, this term. This thing comes back down and gives you integration with respect to the mu theta measure instead of the Lebesgue measure. It's like your points are sampled according to mu theta, but you count this F energy. Okay. So a crucial tool in our analysis that's been used since the beginning of this sort of line of work is what we call the electric formulation. So it consists in reinterpreting the energy, this type of energies, in terms of an electric field. So really thinking a little bit like in physics. And what is the electric field? It's generated from a potential. So the electric potential is just the kernel W, so the Coulomb kernel convolved with the distribution of charges that you see here. So the sum of Diracs at the points minus n mu theta. So I define this. Right? So it's like the electrostatic potential generated by these charges, because W is Coulomb, and now I'm only talking about the Coulomb case from now on. If W is Coulomb, it's just the inverse Laplacian. Okay, so you're solving minus Laplacian equals, so this is just a constant depending on dimension, minus Laplacian equals blah. Okay, and so now if you look carefully at what this definition is, this thing is sort of formally, it's the same as H minus Laplacian H. Because H is the convolution of W with the distribution, and the distribution here is the Laplacian. So I'm tempted to say that this is this, and then use Green's formula, say this is that. Right, so the physicists would not be surprised by this computation. I think they know it very well. The Coulomb energy, the Coulomb interaction energy, is the Dirichlet energy of the electric potential. Okay, so we have this. And now that's kind of nice because you replace a sum of pair interactions by just an integral, a single integral. Instead of having double integrals, you get single integrals, and you can start to look at what is the energy in a piece of space here or here, what is this energy here, here. Except that this is sort of cheating because of the problem of removing the diagonal. So this computation is not valid because you have to worry about the diagonal, and these integrals are infinite. And so what we did is to find a way to give a meaning to all that, and it works through some appropriate truncation procedure, which is a little bit delicate, but now is well under control. And so let me forget about this truncation, which is a sort of renormalization. And let me do as if it's this. And so now I can give you a sort of formal definition of the W I was using before. W is just the limit of these integrals per unit volume. So you integrate, you take your infinite configurations, you compute these H's, you zoom everything, you rescale everything so that it's normalized to have density Y. You integrate over a cube of size R, and you normalize by the size of the cube, and you take the limit as R goes to infinity. Okay, so after doing all that, you define this sort of total Coulomb interaction energy of your Gellium system. That was what was W, roughly. Okay, so now I can talk a little bit about the first result, the next result, we get this way. Is we start to think about precisely, I was trying to make this drawing before, you have your system with many, many points, and we want to understand how much energy of that local energy, you know, that thing that's sort of local in space now, how much energy is in a box, depending on the size of the box, right? How much energy is here, how much energy is there, how much energy is there. Because in fact, if you control the energy, so I would call F sub cube R, or super cube R, it will be this energy F, this integral of grad of h squared, but restricted to the cube. Right? So it's the energy in the cube. This thing actually controls very well the discrepancy between the Diracs and the equilibrium measure. So if you want to count number of points in this cube, well, if you control the energy, my electric energy, you control the discrepancy in the number of points. Maybe not super precisely, but at least something interesting. Okay, so from now on, we're in the Coulomb case only, and there's weird notation you're going to encounter. In order to state correct theorems, I have to define this chi of beta. Chi of beta is a thing that doesn't matter if you're in dimension 3 or if beta is bigger than 1, but it's a logarithmic correction that only plays a role when beta is very small. And I told you I want to be able to consider beta very large or very small. So there's a logarithmic correction which is there probably for a good reason. Okay, so in any dimension in all the Coulomb cases, this is what we get. So this is a theorem that's phrased, sorry, it's a bit heavy to read, but it's phrased at the blown up scale. So, you know, you have your equilibrium measure, you zoom everything so that the support now becomes of size n to the 1 over d, and the distances between points becomes like 1. Okay, so now if you want to look at microscopic boxes, there are boxes that are of size r, with r large but fixed, right? Not going to infinity too fast with n. So if I can take r a sort of constant, that's already the microscale. Assumption here, the only assumption we need is that the equilibrium measure is bounded below. So we have to be in a region where the density is bounded below. It doesn't work in the tails. This theorem. Bounded below and above, that's no other regularity. These are the blown up points. This is the blown up equilibrium measure, thermal equilibrium measure. And we find that there exists a minimal scale, which is defined like this, beta to the -1/2. Only when beta is small, this matters. If beta is large, it's just 1. Such that above the minimal scale, you have good controls. Okay, so basically, the good controls are going to happen all the way down to the micro scale, but the micro scale, actually, the micro scale depends on beta a little bit. So when beta is very small, your minimal micro scale blows up as beta gets very small. Okay, so the interpretation is that basically you have a minimal scale above which things are rigid and below which things should be Poissonian. Means the rigidity only starts to manifest itself once you've passed that scale, and that's, you know, that thing gets interesting when beta gets very small. Otherwise, it's just you have rigidity down to your usual micro scale. And this scale, in fact, is the same roughly up to logarithmic corrections. It's the same as the one I was describing above, 1 over square root theta. That in normal scale coordinates, that's the same, in fact. So that's why I was saying 1 over square root theta is also the minimal scale, the length scale for microscopic rigidity. Okay, so what do we get down to this scale? Where we get that you don't have to read all these statements, but they give you exponential moment controls on the energy restricted to the cubes of size r. It actually is like the volume of the cube. And as corollaries, you get controls on the numbers of points, controls on linear statistics, so very strong concentration estimates near the equilibrium measure, as soon as you are above this minimal scale. Any questions on this? So the idea, there were some previous results, of course. In particular, this Thomas Leblay had obtained something like that in dimension 2. And also Bauer-Schmidt, Bourga, Nicolaiao, also in dimension 2, but it was for beta fixed, and they couldn't go down to the microscale. It was limited to mesoscale. So you had to be, R had to be bigger than n to the epsilon. I remind you here, everything is expressed in zoomed coordinates. So R is always large. Okay, so that allows us to control the number of points down to fixed size boxes. And once you control the number of points in fixed size boxes, it means that you can extract subsequences which converge to limiting point processes. So that was an open problem that was around, that there exists a limit point process, but up to a subsequence. Because you control how many points fall in a box, it's always bounded in a bounded size box. You can get at least a subsequential limit for the point process. So the proof is based on basically proving almost additivity of the energy. So I told you, we have this sort of energy now, we can think of it like that. And what you want to show is that the energy in a union of boxes is the sum of the energies of all the boxes, which is not at all obvious because if you remember from the original formulation, all the points interact, right? So the points in this box, they interact with the points in that box. All the boxes are supposed to interact. However, the energy is almost additive. So what is happening here is that the system screens itself. So that's related to Ross's question. Right? Each box, in fact, contains a certain number of points, but also you should think of it as containing this negative charge, minus nu theta, that neutralizes the points that are in the box. And so from the point of view of a particle that's sitting far, this box is not generating any electric field. Right? So it's because the configurations are essentially screened. So the interactions really only happen locally at short range. And when you're starting to be at long range, you don't feel anything. And the question is to establish this mathematically. So the procedure has been refined over the years, but now the way we think of it in this work with Scott is that we use two different energy quantities. And so two different partition functions, one of which is going to be subadditive, naturally subadditive, and one of which is going to be naturally superadditive. And if you have a subadditive and a superadditive quantity, and you can show that they're not too different from each other, it means that the actual thing is almost additive. So what are these quantities? Well, you want to compute energies again in the same form as that, integral of grad u squared or integral of grad v squared. But now we'll restrict to a cube. And one of them we solve with Dirichlet boundary conditions. So it's the same equation, right? Minus inverse Laplacian of blah, except we solve with boundary conditions. And this one's with 0 Dirichlet, this one's with 0 Neumann. So when you think about it a little bit carefully, you find that the first one gives you something subadditive and the second one gives you something superadditive. The second one is only actually meaningful if the number of points in the cube is exactly the volume of the cube, otherwise you cannot solve this PDE, as our PDE students know. Okay, so we have these two quantities, one subadditive, one superadditive. We can define the partition functions that are associated with this energy for each given beta, so we call them Kn, that's for the Neumann one, and Ln for the Dirichlet one, roughly. You can divide by the volume, and because of the sub-superadditivity property, what you find is that the log Kn over Rd is behaving like that as R goes to infinity, so this is R. And the log Ln over Rd is behaving like that. One of them is, one is above the other. That's not too hard to show. So they're in fact converging. each of them to a limit, but you can show it's the same limit, because what you can do is you can show that the discrepancy between the two is not very large. And what we can show is that the discrepancy is like 1 over r, in fact. So how do you do that? Well, that consists in showing that, in fact, these boundary conditions, they don't matter so much. Like changing the boundary condition doesn't change so much the thing. And why is that? Well, in fact, the boundary conditions only matters near the surface. So as soon as you're sort of well inside, it shouldn't matter very much. That's why you expect a contribution r to the d minus 1. And when you normalize by volume, that's why you expect a 1 over r. So it's a surface contribution. And how to prove that is what we call a screening procedure. So again, that's related, I think, to Russ's question. What you show is that you can take a configuration given to you by a problem like this, and you can transform it into a configuration that satisfies the Neumann data by changing it only near the boundary. And that makes essentially that makes effectively the thing screened for the outside. It means that once your configuration solves this, when you sit far away, you don't feel any field generated by it. And so the screening procedure is quite, it's quite technical, but it allows you to show that you can do this replacement one into the other without changing the energy very much. And so these two things are not so different. And what that shows is that the original true energy, which satisfies neither Dirichlet nor Neumann, it's somewhere in between. It's actually precisely somewhere in between. And so it has to converge in the same way to the same limits with a rate. Now we get a rate, 1 over r. And the limit, we call it f of beta, because it's a function of beta. Okay, and this f of beta, you can characterize it as the minimum of the rate function that we had defined with Thomas-Leblé. So I don't want to bore you too much with all that, but now, thanks to that, with this idea of almost additivity, we can get an expansion of log z with now an error term, which is better than what was known before. So previously, so we have the order n term, as I told you. So the order n term is explicit. It involves this function f of beta. And f of beta can be characterized as this. And now, instead of knowing that the error term is little o of n, we can get that the error term is an explicit power of n, which for now is 1 minus 2 over 3d. So it's not optimal at all, but it's sufficient to do something with it. And in particular, what we do with it is to obtain central limit theorems. Any questions on this so far? No, so this is sort of in the direction of the, these conjectures by the physicists about the free energy expansion. So yeah, you know how the partition functions depend on the equilibrium measure, and everything is relatively explicit down to order n. Okay, so the last results are about proving central limit theorem for fluctuation. So this is the result we had obtained previously with Thomas-Leblé. It was restricted to dimension 2. You take a test function, you assume it's smooth enough. So how smooth is here? So like, let's say 4 derivatives or something. You look at the linear statistics, and you can show that this converges to a Gaussian. So without normalization, you see this is very different from IID random variables. You don't need to normalize. This converges to a Gaussian with a certain mean and a certain variance. And if you forget about this superscript sigma, you see the variance is integral of, it's like gradient c squared. That corresponds to GFF essentially. So this is the structure of the GFF correlations. So what converges to the GFF is this inverse Laplacian of this difference. That's exactly my electric field before, electric potential, sorry. Okay, so this shows a very, very strong, another way of quantifying a strong rigidity of these systems. And you can take test functions which are localized down on small scales. So in this result, we have down to mesoscales. And the support of the function could overlap the boundary of the support of the equilibrium measure. So there was a very similar result by Bauer-Schmidt, Bourgade, Nicolas, and Yao. But again, only down to mesoscales. So now things have improved a little bit. And I can do two things, go down to microscales and also do it in 3D under some additional assumption. And also other things, also for these regimes of temperatures that are possibly very small or very large. Okay, so I want to show you this theorem. I think that's the nice conclusion. So in dimensions 2 or 3, V smooth enough, the test function smooth enough. Let's not discuss that. In dimension 3, assume in addition that this free energy function is quite regular. That's a strange, that's an assumption that I cannot justify, but it corresponds to something like saying near this beta, you don't have a phase transition because the free energy as a function of beta has to be smooth there, and you have some good estimates in case beta is very large or very small. And now this assumption, that's the length scale down to which I'm going to be able to prove the CLT. This length scale has to be much bigger than the minimal scale. So this is quite natural. Again, minimal scale is a sort of barrier. Below that, I don't expect rigidity. Above that scale, I expect rigidity. So this is essentially down to micro scale. Now we can go down to microscale because if beta is fixed, this rho beta is 1. This assumption, beta can depend on n. So it can be very small or very large, but not too large. If you get very, very large, this is a very large number, it fails. And this assumption, just to say that you cannot be too close to the boundaries. You have to be a bit inside, like a good bit inside the thing. Just something very small is here. Okay, then there's some suitable normalization of your fluctuation, of your linear statistics minus the limit. And this is with respect to the thermal equilibrium measure. This is what allows you to go down to very small betas, possibly. There is some suitable normalization. There is some suitable mean that you have to subtract such that finally you converge to another Gaussian with the same variance, grad C squared. Okay, so again, it's a GFF type convergence. First time you have a result in dimension 3, but under this assumption. And the method of the proof, it's borrowed from the previous paper with Thomas Leblay. It's a transport-based method where you have to compute. So I will go fast on comparison with the literature, sorry. But you have to compute the ratio of two partition functions, one for perturbed potential V, Vt, and one for the original V. And so that's where we use the precise free energy expansions that were obtained before. So the fact that this theorem there, I'm gonna get to it, was obtained with a good remainder term, that's what allows to get the CLT. And if I could get a remainder that's even better in terms of the power here, the CLT would apply to a larger dimension. So dimension 3 is only a limitation because of the quality of the exponent here. But dimensions 4, 5, 6, etc. would be possible with a better exponent. Okay, so I'm already over time, so I will stop here. Thank you for your attention. Are there any questions at this point? Or maybe I shouldn't be the one asking them.
Sylvia, I have one question. If you look at discrete lattices or versions of log gases that involve discrete lattice, or these kind of deformed versions that like Elise and Alexei and Vadim have looked at. Is there any hope of establishing these sort of global descriptions of minimizers and variational formulations for these global versions?
I think so, in fact, yes. I had briefly discussed this with Vadim, and we concluded that it seems doable to carry out the same program. You just have to redo all the steps, following the same lines of ideas, but I don't see a reason why it wouldn't work. It's just very tedious, let's say. But yes. At first, I thought there could be shortcuts due to the fact that you have this discreteness, you can only take certain values, But in fact, there doesn't seem to be a shortcut. So you just have to redo everything, in particular the screenings and everything has to be done again. It just takes courage.
Thanks.
And time.
Sylvia, in your result with Scott and the corollary that you said, there exists a limit. I mean, you have estimates, and I guess that what you're saying here that you have tightness, is that your local limit thing is tight. So but you cannot, you don't have uniqueness of the limiting thing.
No, that's the problem.
And you don't have, so it's not like in the paper with Leblay where you had this LDP for the full empirical field. Here, you don't have a variational characterization of what the limit thing would be.
Yes, it's a little bit different because the paper with Thomas, the thing is averaged. So the process is after averaging. So it's naturally made stationary. Whereas here, you really fix a point and you blow up.
Yeah.
Okay, but in any case, even in the thing with Thomas, we don't have uniqueness of the minimizer of the rate function.
Okay, but you have a description as a variational problem, but you're saying you're not sure that it's unique.
No, except in 1D. So in 1D, Thomas was able to prove that there is uniqueness. And by a very nice displacement convexity argument. And so that comes back to sin beta. Sin beta is the only minimizer in 1D, but as soon as you're in 2D, there could be several minimizers. It's not even, it should be normal that if there's a phase transition, for example, you would have several minimizers.
I see. I thought in fact, you had already this uniqueness. I didn't get it. So, because of course, then the next question would be, once you understand very well like this, the local thing, are there hopes or maybe already results about universality? Let's say D equal 2. I don't care about D equal 3. So you take now a matrix, but you don't assume that it's G libre. Is there a hope that the local limit looks like what you're describing?
So, yeah, I mean, I don't know if what you're talking is the analog of what's known in 1D. So in 1D, you have universality with respect to D, right? It's the Bourgaert-Derbeau-Chiao theory. And Becker-Mas-Galli-Dionnet. So it means that in fact the mu V, V only determines the macro behavior, but the microscopic thing is universal. And in 2D, that's also expected, but it's much harder. I think, yeah, it's plausible, but it's no one has succeeded yet.
And by the way, the question I asked during the talk, Paul had a good catch. A real G libre is not beta equal 1, it's beta equal 2 with a extra constraint, which is of course this thing around what I was saying, the thing around the real axis.
Okay, thank you, Paul.
So is this also true even in dimensions 8 and 24, where they explicitly characterize the zero temperature minimizers? You can't characterize in positive temperature, like what the law has to look like?
I mean, the results I presented to you are for any dimension, right? You're asking about this LDP?
Well, it's about the variational problem, or the law of the local picture. Okay,
Yeah, everything I described is in any dimension, so it includes 8 and 24, but other dimensions as well. The only place where we're stuck is the CLT, because that's basically the surface error terms become too big when you're in large dimension. So additivity, almost additivity doesn't buy you very much in high dimension. But otherwise, yeah, I don't know if there's a lot of physical interest in dimensions 8 and 24, but the people actually in approximation theory, they care about large dimension for theoretical computer science. And our colleague Oded Regev, so he looks at these problems in large dimension. That's what he cares about, these crystallizations in large dimension.
Any other questions?
Yeah, I have a question related to Ivan's question. So it seems to me your results combined with Leibniz results, you can give a new proof for the Bach universality for the beta ensemble, independent of Virac their result.
Oh.
No, I mean, if you're talking about the universality of the local statistics and things like that, no, we don't really do that.
But you can characterize it by the variational problem. And you mentioned the result gives the uniqueness of minimizer in the 1D.
Yeah. So it's slightly different from what you say, I think, but it's characterizing the point process. Right. So then, if you want to go from the point process to all the local statistics, that's not so obvious, I think.
Awesome. So basically, you will have like for any potential V, for the 1D at a fixed beta, the point process is unique given by the sign beta.
Mm-hmm.
I wonder because there's also the discrete beta ensemble for the 1D case. So this will potentially also give the same conclusion for those 1D discrete.
So that's the Ivan's question, right? You're talking about the same discrete guys?
Yeah, because for that one, it's not known what is the Bach statistics. Do you think this approach will give us at least like a universal, like the point process is unique and you can characterize it?
Yeah. Okay, so maybe it's a motivation to have the courage to do this discrete thing. Yeah.
Thank you.
Thank you.
All right, should we thank Sylvia again?
Well, thanks for the invitation.
Have a good evening.
Yes, have a good rest of